Okay, so hello and welcome all to our October Womeesa seminar. My name is Fernanda Alvarado, based at Monash University, and I am a member of the Womeesa committee. And today I am hosting this seminar on behalf of Lorna Strachan, this year's Womeesa seminar series coordinator. I begin today by acknowledging the traditional owners of this land in which I am today, the Wurundjeri and Bunurong people of the Kulin Nation, and recognizes their continuing connection to the land. And as Womeesa is an international organization, we also pay our respect to the Maori, Astangata, Whenua, and Te Tiriti o Waitangi partners in Aotearoa, New Zealand. We pay our respect to their elders past, present, and emerging. Indigenous people were the first Australian and New Zealand earth and environmental scientists, and we have a lot to learn from their deep knowledge that spans tens of thousands of years. The Womeesa seminar series is about showcasing the amazing work of women in earth and environmental sciences in Australasia. All the recordings of past seminars are available on our website. You can sign up as a member of Womeesa to get a notification of upcoming seminars, or you can follow us on Twitter and Instagram. I am delighted to introduce our October speaker, Dr. Christina Reisselman. Christina is a senior lecturer in the Department of Geology and Marine Sciences at the University of Otago, a veteran of 8 Antarctic and Southern Ocean expeditions. She's a co-PI of the New Zealand and Antarctic Science Platform Project 2, Antarctic Oceans Mechanics, Past, Present, and Future. And she currently serves on the Science Committee of the Australian and New Zealand International Ocean Discovery Program Consortium. Today, she is going to talk to us about how warm is too warm for Antarctica. And it's my pleasure to hand you over to Christina. Thank you so much.
Thank you so much, Fernanda. Kia ora, ko Christina Reisselman, toku ingoa. My name is Christina, as Fernanda says, and I'm here at the University of Otago in Dunedin, New Zealand. And I'm really excited to be with you today to take a little informal jaunt through one of my favorite topics in the earth science, which is trying to understand how Antarctica responded to and played a role in driving climate the last time that our planet was in a situation similar to what's projected for the coming century. So I'll touch over the course of the hour on some highlights of my career and areas that I'm really excited about. And then because of, I guess, this venue and having been privileged to attend Lorna's seminar a few months ago, I also want to touch on a couple of things that are lowlights of my career when we get to the very end. Just acknowledging some of the novel challenges that women in the earth science have faced for too long, and my ambition that those challenges will be less a part of careers to come. So we will kick things off here, and we're going to start with carbon dioxide, right? So my research is largely in using marine sediments as a time machine to understand how climate has changed in the past. And it won't be a surprise to any earth scientist, nor really any human on Earth right now, that atmospheric CO2 is a major contributor to shaping the climate that we live in and to shaping the climate that we are looking to be faced with in the future. So we're going to start with some CO2 molecules and then just think for a few minutes about how the composition of Earth's atmosphere and the amount of CO2 and other greenhouse gases in Earth's atmosphere sculpts the climate of today, right? So the greenhouse effect, this I imagine is familiar to all earth scientists. The key that we're contemplating is that the amount of CO2 in the atmosphere impacts the amount of heat that's trapped and retained by greenhouse gases. So radiative energy enters the atmosphere. The Earth generates energy in response. And the more greenhouse gas we have in the atmosphere, the less of that heat makes it back out into space. And of course, CO2 is rising. The most recent measurements of atmospheric CO2 made from Mauna Loa. So this is the location where CO2, we have the longest continuous history of CO2 monitoring on the planet. So monitoring since the 1960s. As of September, so last month, that's the last complete month of data we have, atmospheric CO2 concentrations sit at 415 parts per million. Now, I've been imagining or thinking about the earth sciences since the late 1990s, and really paying close attention to where CO2 sits, probably since the earliest 2000s. And it sort of, I guess, gives me a little bit of frisson, knowing that the first time in the last 3 million years that CO2 concentrations in the atmosphere rose above 400 parts per million was in 2013, right? So for the past 3 million years, CO2 sat consistently below 400 parts per million. And since 2013, when we first crossed that threshold, we've been continued to track up and up and up. So what does that tracking look like? We have this is a little bit of a long video, but I think it's a really nice way to sort of position what we see in terms of modern CO2 in a longer context. So what we're looking at here, we've got this red station. This is Mauna Loa, the location of that continuous atmospheric CO2 monitoring since the 1960s. Here, the clock started in 1979. So this is essentially the CO2 of my lifetime. I was born in 1977. So this is how the trajectory of atmospheric CO2 has unfurled for almost the whole time I've been on Earth. So we've got the Mauna Loa record here, that's in the red dot, and you can see that dot bouncing up and down and getting gradually higher and higher. So when we see the dot rise, those are Northern Hemisphere autumns, when plant matter in all of this massive Northern Hemisphere landmass is dying, decaying, releasing CO2 into the atmosphere. When we see the dot fall, that's spring in the Northern Hemisphere, where plants are growing, leafing out, generating these amazing boreal forests, sucking lots of CO2 out of the atmosphere. So that's what we see in this sawtooth pattern going up and up and up. But you can see that that sawtooth pattern is superimposed on this regular march toward ever-rising CO2 values. Now, all of these light gray dots are local stations. This blue dot, that's our South Pole, right? So another location that CO2 has been constantly monitored. And then we're adding in older data, right? So we've got more data from Mauna Loa in that continuous Keeling curve. Now we've got ice core data peeling in at the bottom here. And you can see that our axes are really compressing toward the top. So we're just tracking the CO2 as we move deeper and deeper into the past, so 60,000 years before the Common Era, 100,000 years before the Common Era. Now we start to see so we've got our glacial maximum, very low CO2 values down here around 280 parts per million, and then the suite of previous interglacial periods. And what you'll see is that nowhere in the last 800,000 years, so that's the time period encompassed by ice cores. I might just hop us back here and pause so we can take a good look, right? So we've got a couple of different ice core records. We have some high resolution ice cores. We have those Keeling data, and then we have the bigger picture of global CO2 since we started taking discrete atmospheric measurements. And from this pump handle video, this is a product of the US National Oceanic and Atmospheric Administration, their carbon tracker. And this is something that they update periodically. You can find it on their YouTube channel. And what this really demonstrates beautifully is that the circumstance that we're in right now is so far outside the range of natural variability for the last entirety of ice core records in the last 800,000 years in this diagram, that really we would expect to see no climate analog over that last 800,000 years that we could use to tease apart and to understand a little bit more about what we might be looking at in our global future, right, in our climate future. So in order to look, before we go looking further into the future, I'll just say, so this is a much shorter record. This is a record that starts in 2002. And once I click play here, what you'll be looking at over on this map of Antarctica, so these are now satellite data, and this is looking at the surface lowering of the Antarctic ice sheets. And the colors that you'll see will end up being equivalent, I guess, elevation changes measured in their equivalence for the meters of water, right? So I'll click on this here and you'll see that at the same time, the same rate that we saw that CO2 climbing and climbing and climbing on that pump handle diagram, you also see some regions of the Antarctic ice sheet lowering and lowering and lowering, in some cases really rapidly. The places where we see the most rapid lowering of that ice surface are over here. This is the West Antarctic ice sheet. It's divided from the East Antarctic ice sheet across the Transantarctic Mountains here. And then you can see that there are a couple of places where we have these ice stream lines leading to significant lowering on the margins of the East Antarctic ice sheet. So we know we can, it's self-evident that as CO2 is rising, Antarctic ice mass is being lost through changes in global surface temperature. So when I think about how my research sort of nests within the suite of things that humans care about, I find myself thinking quite a lot about the Paris Agreement. So this was a gathering in 2015 of leaders and policymakers from most nations of the world. It was a response, I think, to the challenges that IPCC, the Intergovernmental Panel on Climate Change, was facing. So IPCC is excellent at documenting change and at generating projections and scenarios for possible future climates and global futures. But this Paris Convention really got into the nitty-gritty of comparing how national policies to mitigate climate change, so how those national policies and the changes in atmospheric CO2 that were represented by that policy making actually played out in terms of global temperature change. And one of the sort of key principles of that Paris Accord was the idea that it was really fundamental to fundamental to maintaining a reasonable standard of human life on Earth, to maintain global warming to a maximum of 2 degrees warming above pre-industrial levels. And so that the Paris signatories would do everything they could as nations to set policy that would maintain that 2-degree threshold, and that there was a commitment to attempt to keep temperature increase below 1.5 degrees, right? So absolutely hard ceiling at 2, but better to keep below 1.5. And for me, as a person who thinks about how Antarctica has changed in the past, I'm real interested in what that difference means, right? So 0.5 degree seems like not a great deal. I'm here in Dunedin. A week ago, we had 3 centimeters of snow on the ground. 3 days later, it was 19 degrees and sunny outside. So 0.5 degree, and when we sit inside our sort of daily weather patterns, 0.5 degree seems like it's really not that big a deal. Is it that big a deal? So what we're looking at over here on the left side of the slide is essentially a summary. This is the most recent update. So November 2021 is the most recent update to this climate action tracker. This is a group that monitors nations' progress toward the Paris Agreement. And every time a suite of new policies are announced, or anytime there's one of these big climate conventions, this tracking organization rebalances and recalibrates where those CO2 emissions targets would land us in terms of projecting temperature rises, right? So as of November 2021, and that's a while ago, it's almost a year ago, the current policies in place around the world, including all of the Paris Agreement signatories, if those policies were allowed to play out ad infinitum, the average estimated temperature increase above pre-industrial attached to that suite of policies would be 2.7 degrees C, with an upper limit of 3.6 degrees C and a lower limit of 2. The targets that nations are committing to for 2030 would pull warming down to 2.4 degrees C. Pledges for future change might get us down to 2.1 degrees C. And the best case scenario, right, assuming that full implementation of all announced targets, including New Zealand has a target to be net zero in terms of CO2 or greenhouse gases by 2050. So if we successfully achieve all of the most ambitious targets that are presently under consideration by nations, we would be looking at a most optimistic scenario of 1.8 degrees C warming over pre-industrial values, right? So what does that look like? I'm just gonna collapse you guys for a minute. So over here, this is again from the Climate Action Tracker. In order to maintain temperatures that were consistent with a 1.5 degree sort of, we think as a world that this is our best, I guess, our best opportunity to stave off really catastrophic impact, right? So the gap between our ambitions and pledges and targets and the greenhouse gas emission rates that would be consistent with limiting our warming to 1.5 degrees C is pretty significant, right? So it's on the order of 20 gigatons of CO2 emissions equivalent per year. So somewhere in all of our policies, we need to find an additional 20 gigatons of carbon savings by 2030 in order to get ourselves onto that track. So seems like a pretty steep climb. And I guess the question is, how important is it for us to make that steep climb, right? How urgent is that situation? And my favorite tool as a geoscientist to confront that urgency and examine that urgency is by reconstructing analog climates of the past, right? So what we're looking at here are the current CO2 levels. This is actually current as of 2011, so it's a little bit further up even still. Oh, no, that's actually a lie. This is current. Sorry, this is current. And you can see how elevated above our sort of peak interglacial CO2 from past interglacials that current position is. And you can also see the sort of drumbeat of the overall dominant drivers of climate cycles operating on this record, right? So we have a variety of changes in Earth's orbital configurations that cause this climate metronome and have governed the pacing of that climate metronome for tens of millions of years. Right now, we see the most dominant cycle is this eccentricity cycle, or so how circular or how elliptical Earth's orbit is around the sun, which influences whether sort of the distance between how much solar radiation Earth gets when its axis is pointed toward the sun at a close pass versus a distant pass, right? So those close and distant passes govern our peaks. And right now we're sitting in roughly 100,000 year climate cycle dominated by that eccentricity band. And you can see that even with CO2 not varying a great deal, it's enough to develop whole-scale ice sheets in the Northern Hemisphere during far passes with slightly lower atmospheric CO2, right? So we have our glacial minimum atmospheric CO2 at about 180 parts per million in pre-industrial times, interglacial maximum at about 280 parts per million in pre-industrial times, and that there's a really tight covariance between temperature and CO2 on those timescales as recorded in ice cores. So what does all this have to do with Antarctica? I think it's clear what it has to do with Antarctica. My entrance to being really interested in this disparity between where CO2 sits now and what our sort of constant, I guess that constant drumbeat of past climate has looked like within the geologic past was through a really positive experience as an undergraduate at the University of Otago, at the University of Nebraska-Lincoln. When I first encountered this debate, this is what has been called the serious debate in the past, although I think at this point the debate has softened a little bit, was initially sparked in the 1980s. And it was sparked by the discovery of a series of glacial deposits. So here we're back in Antarctica, right? Those are those trans-Antarctic mountains slicing through here that separate the West Antarctic ice sheet from the East Antarctic ice sheet. And you can see these numbers in here, 1, 2, 3, so locations on the East Antarctic ice sheet side of the trans-Antarctic mountains. Here's a number 4 down here. Where in all of this these glacial deposits, some chunks of marine material were identified, right? So these clasts that contained a whole range of marine fossils, foraminifera, diatoms, radiolarians, sponge spicules, ostracods, also some southern beach leaves, bits of wood, fish fossils, mollusks, insect fossils. So quite a diverse array of fossil material found in these clasts of glacial debris. So what we're looking at in this map is a 1984 reconstruction of what the Antarctic continent would look like if the ice sheets were peeled back. You can see that we've got this area in the Aurora Basin where today's ice sheet would be grounded below sea level. In the Wilkes Basin over here, where today's ice sheet would be grounded below sea level, and then a lot of area around the West Antarctic margin where the ice sheet would be grounded below sea level. And the sort of controversial concept proposed to explain the presence of this diverse marine flora and fauna, along with leaves and other indications of a warmer planet in these locations that today are situated firmly beneath a 3-kilometer thick ice sheet, was that in the past, there had been open marine seaways connecting along the back of this mountain range. And the age of that open marine, I guess that hypothesized set of open marine conditions was determined using fossil diatoms, right? So these are some of the most controversial microfossils I'm familiar with. This work was the PhD research of David Harwood, who was a really important mentor of mine and as an undergraduate at the University of Otago. That's the second time I've said that, as an undergraduate at the University of Nebraska. And David was, when I encountered David, I was an English major who was geology curious. And I had a really interesting conversation with him after class one day about what he did. And what he communicated to me was that this work that he was still in the midst of in the 90s when I was an undergrad, was the center of this quite furious debate about how long this piece of the Antarctic ice sheet had been in its current stable configuration. Right? So there's one school of thought at that time that the East Antarctic ice sheet had been frozen solid, essentially with the boundaries it has today, at essentially the height it is today for the last 14 or so million years, right? So that it hadn't seen any significant decrease in size for through huge fluctuations in atmospheric CO2 and temperature. And then there was this sort of contrary argument and controversial argument that David had waded into as a PhD student and was continuing to explore when I was an undergraduate, that the age of these microfossils, which were late Pliocene, so around 3 million years old, that the age of these microfossils could be used as an indication that there must have been open marine conditions 3 million years ago, the last time atmospheric CO2 was elevated to about 400 parts per million, in order for that marine material to find its way high onto these mountains. So there would have had to be open seaways, deposition on the seafloor, and then advancing ice at some point later would have bulldozed some of this material up onto the flanks of the mountains. And for me, that was, really a shocking thing to learn, that we didn't know how stable that ice sheet had been the last time atmospheric CO2 sat at 400 parts per million, right? It seems like a fundamental thing to understand. If you want to be able to project the impact of future climate change, gosh, you really have to know how Antarctica behaved the last time climate was similar. So that was a real eye-opener. That was the instant I discovered that science is all the things we don't know yet and not just memorizing things we do know. And I think for me, that conversation redirected my career. And I am incredibly grateful and will always remain grateful to David for sharing that insight with me and for supporting me as I've continued, in fact, to work in Pliocene diatoms myself. Right. So that brings us to, we're outside of the ice core records. We're now flipping a figure. This is a bit of an old figure from a science plan for the International Ocean Discovery Program back from 2013. The new version of this plan is in progress. See some good friends from the Australia New Zealand IODP consortium out there. So as those folks will know, we've got a sort of a big new vision in front of us for future ocean drilling. But some of the things that we're thinking about here today and some of the things we were thinking about in 2013 remain really fundamental to understanding our future directions. And key among them is, so here we're now looking at, we flipped the axis. We've got today over here on the left, going into the past on the right. In this top panel, we have atmospheric CO2. So CO2 in 1830 at this black bar, in 2011 when the figure was made, in a slightly higher black bar, and then I've slapped 2022 on there, just so we can see how rapidly we're tracking up above 400 parts per million. And as you look into the past, you can really see you have to go 3 million years into the past to find a prior time when atmospheric CO2 was up here around this level. So that turns out to be our best analog to understand how climate, so overarchingly, how climate responded to a planet with CO2 at 400 parts per million. It's a really nice analog for a number of reasons. Key amongst them is that continents and ocean basin configurations were quite similar to what they are today. So no weird seaways, no super expanded continental shelves, nothing. Most of the mountain ranges that we have now were in sort of the same places. So a reasonably near tectonic setting to what we're looking at today. An alarming way in which this is a pretty reasonable analog is that the Northern Hemisphere was largely unglaciated. And if you follow the news, you'll know that ice retreat is rapidly underway in the Northern Hemisphere today. So we're sort of on a bullet train toward a climate that the Pliocene becomes a better and better analog for with every passing day. And then many modern plants and animals had evolved by the time we enter this analog period. And that means that we can look at distributions of plants and animals today compared to plants and animals from 3.3 million years ago, and assume that their distribution is reasonably analogous. A couple of other great things about this period. that it's pretty easy to find in the geologic record. So here we've got oxygen, the benthic oxygen isotope curve, and you can see the series of interglacials, sort of three little peaky interglacials that are the last time the benthic isotope system sat above roughly where it is today. So those are really easy to track down. It's also bracketed by a couple of paleomagnetic reversals that are always really easy to find in the geologic record. So all of those things together make it a really appealing analog to go back and reconstruct a lot of things about the planet from this time, this prism interval. So this is the interval that's been a big focus of the US Geological Survey for many years. And it's the Pliocene. I'll have to come back to you once I've thought a little bit about what this acronym stands for. What it generally is understood to encompass is three key interglacial periods. So these three interglacials right here, and right here. So looking at sort of the average temperature and global climate setting across those three interglacials that go from about 3.3 to 3 million years ago. And the key thing that I'm interested, or one of my key interests in this particular time period from a particularly Antarctic perspective, comes from the reality that as temperature rises and we see continental ice mass loss accelerating, the West Antarctic ice sheet today, if you melted the entire thing, that would raise global sea level by about 3.3 meters. The East Antarctic ice sheet, that's the one that we understand to be more stable, although was also the focus of this serious debate. That thing holds about 53 meters equivalent sea level, right? So it's about 3 kilometers thick, maybe up to 4 kilometers in its thickest area. And so even a little destabilization from this ice sheet has the capacity to contribute to a major sea level rise. Right. So my favorite tool to explore these questions is through paleoceanography. For me, I view this as a polar ocean time machine. So I've got my favorite drill ship, the JOIDES Resolution, up here on the top of my slide. Drops the drill string through the moon pool into the sediments and shoots sediment cores. So each of those cores returns a record of what's going on below the seafloor. And the parts of these records that I'm the most interested in are the microfossils. So the diatoms are my fossil group of preference. And then I also get pretty excited about the geochemical signals that are preserved within those biological materials, right? So that's the suite of tools that I like to use to reconstruct how the ocean has behaved in the past. And so using this time machine, right, using this global network of marine sediment cores, most of what I'll tell you about today was collected by this drill ship, the JOIDES Resolution. But there are also some cores in here that have been collected from floating ice platforms. So we'll talk about that a little bit as well. So what we're going to do for the next probably 10 minutes is tick through 5 things we know about the climate 3 million years ago, at that time when CO2 was up above 400 parts per million. And we'll see how those 5 things we know, I guess what they tell us about the difference between a 1.5 degree temperature rise and a 2 degree temperature rise in the context of our current global warming. And the first thing we know, and this I don't think is a surprise, but it definitely bears displaying, is that if you have an atmosphere with 400 parts per million in it, or parts per million CO2 composition, the planet is going to be warmer, right? So this, what we're looking at here, is a series of individual point reconstructions from a whole bunch of ODP and IODP sites, right? So each of these is from that little sliver of time, that prism interval, those 3 key interglacials about 3 million years ago. And you can see that, so each of these spots is a different reconstructed temperature of that part of the global ocean during interglacials at that snapshot in time. And we're further looking at this as an anomaly plot, right? So where we see sort of uncolored circles, right? Here's a location with pretty much no color to the circle. That's a place where the Pliocene Ocean was almost exactly the same temperature as today's ocean. Any place that you see a blue circle, so this one's pale blue, that means that the Pliocene Ocean was a little bit cooler than the modern ocean. There's a little bit of that here around Florida, a little bit here in the Mediterranean, some places where the Pliocene Ocean was a little bit cooler. And then any place you see these warm colors, and in these burgundy hues, that's up to 8 degrees temperature anomaly. So we have locations up here in the Arctic where reconstructed Pliocene sea surface temperatures were 8 degrees warmer than they are today, right? And one of the things that you probably have already identified on this map is that warming was heterogeneous around the globe in the Pliocene, that it was concentrated in the northern hemisphere, that there was some warming in the southern hemisphere, a little bit more in the southern hemisphere than at the equator. And if you sort of average this out, and this is not, I think this is a good indication or a good demonstration of why this idea of an average global warming isn't actually that useful. The average temperature of the planet was about 2 degrees warmer than pre-industrial temperatures during this analog time. Right, so you can see that a global average temperature increase is actually, there's no such thing as an average place on the globe. But if you average these together, you get 2 degrees of warming, and that makes this a really nice interval of time for us to contemplate when we're thinking about what an average 2-degree warmer planet might look like in the context of modern climate change, of current climate change, right? So we know 3 million years ago, CO2 was about 400 parts per million. We know the globe was about 2 degrees warmer than present, and warming was amplified at the poles. So that's the first thing we know. The second thing we know is that ocean circulation was a lot more sluggish, and that, in fact, the places where deep water was forming around the planet were really different. So I might just use speaker's prerogative to flip back here to this this map of sea surface temperatures. So you probably are familiar with the concept of thermohaline circulation. You know that in the poles today, where the ocean is very cold and sea ice is forming, pulling fresh water out of the surface ocean and concentrating salts, that produces a really dense surface water mass. Dense surface water sinks below less dense water and generates a thermohaline circulation around the planet. So here we're looking at thermohaline circulation with Antarctica sitting in the middle. It's the only part of the planet where seawater can circulate around the full zonal, I guess has full zonal circulation around Earth. And you can also see here that we've got a couple primary areas of deep water formation on the planet. So these places where water is purple or deep purple, those are areas where we have that cooling and brine rejection causing water to sink and driving that big global conveyor belt. So today that happens in the northern hemisphere up here in the Arctic, also happens in some of these areas in the Antarctic, places that we have a lot of sea ice production. We see a lot of deep water formation. And one of the things we know is that today, water subducting from the Atlantic Ocean gets as far south as 40 degrees before it's incorporated into this circumpolar current. What we see if we look 3 million years ago, so this is a little bit of a complex figure, so I'll walk you through it. What we're looking at now is depth in the ocean from a location right around here, right? So pretty far to the south, and we're using neodymium isotopes as a tracer for what water mass sits in what part of the global ocean. The key things that you'll want to see in this figure are that today, water from the North Atlantic has a neodymium isotopic composition of about -13.5, and water in the modern Antarctic, so deep water formed from around these areas, has an epsilon neodymium composition of about -8. So where you see in this blue line, these are modern water column data, right? So people just dipped a CTD into the ocean, they snapped some bottles of water, brought them home, analyzed the neodymium isotopes, and you can see that even this far south, we've got this blue line showing Antarctic intermediate water. So we're pulling more toward the modern Antarctic value up here at around 1,000 meters. And then as we get deeper in the ocean, this big bulge moving back toward this light blue line shows us that North Atlantic deep water is pulling our isotopic signature. These are fingerprints of different water masses. So we've got that fingerprint of North Atlantic deep water around here at 3,000 meters deep in the ocean. And then we see the influence of Antarctic bottom water coming in the very deepest parts of the ocean. So that's what the modern ocean looks like, right? Can see that impact of really efficient formation of North Atlantic deep water. If you look into the Pliocene, so these are 3 reconstructions from 3 IODP sites around the Meteor Rise area. And what you can see, so our end member water masses from the northern and southern hemisphere were a little bit different in the Pliocene. We've got our proto-North Atlantic deep water over here at -11. We have our proto-Antarctic deep water over here at -8. And what you can see is that all through these key depths in the water column that today have a lot of North Atlantic water fingerprinting, in the Pliocene, there's no hint that water sourced from the Atlantic basin reached these parts of the ocean at all. And so we infer from that the quite warm surface in the North Atlantic made deep water production much less efficient, that there are some other indications from carbon isotopes that overall circulation was more sluggish, and in general that Southern Ocean waters were dominating that circulation, right? So we know in a planet with 400 parts per million CO2 in the atmosphere, it's about 2 degrees warmer. That warming is just sort of heterogeneously distributed with polar amplification that reduces the formation of North Atlantic deep water. And that means that our ocean interior, the heat distribution is considerably altered, right? So that's the second thing we know. The third thing we know is that the ocean around Antarctica specifically was warmer, right? So this is some work, I should say, this neodymium isotope work is work that was part of my postdoc at the US Geological Survey. That is still in prep, but is a cool piece of science that I'm excited to put out now that my teaching load is starting to moderate. This is a really exciting piece of work that was driven largely by my honors student, Briar Taylor Silva, using diatom assemblages to explore the position of fronts in the Southern Ocean, also during this key period of time. And so what Briar discovered, she used diatom assemblages and some indicators of subantarctic temperature to find fingerprints of warm circumpolar waters from this site, IODP U1361. And then she incorporated some prism sites and reevaluated those data to track that warming signal around the continent, and found fingerprints of warm circumpolar water that came quite close to the marine-based East Antarctic ice sheet, again, during that key time interval 3 million years ago. So what we're looking at today is the modern distribution of those fronts. We've got the sea ice zone here close to the continent, the polar frontal zone in slightly darker blue, and then the Antarctic circumpolar current and the subantarctic front to the outside. So if we reconstruct the past using these diatom assemblages, what we see is a modest contraction of that polar frontal position during most of the Pliocene. And then during this sort of pink interval is the additional retreat of the polar frontal zone associated with that key warm climate interval when CO2 was at 400 parts per million. So that reconstruction shows us that we had subantarctic waters in quite guess, quite a close juxtaposition to that vulnerable ice sheet during this key climate interval. And one of the things that's important about that discovery is that the position of those fronts today are largely governed by the shape of the seafloor. So what we're looking at in the rainbow here, that's the bathymetry of the Southern Ocean. And all of these black squiggles that's a series of 15 years of data of the 1 degree C, or the -1 degree C isotherm position at its maximum northward extent. So that's essentially the temperature that seawater freezes at. And so you can use that 1 degree C boundary to estimate where water could reach freezing over a series of years. And then this white line is the average sea ice position over that same set of years. And you can see that here along some of these spreading ridges, over here, the Australian Antarctic ridge, and then creeping through from, I guess, no, this is the Pacific Antarctic rise, my apologies. And then over here, south of Australia, that set of spreading ridges really steers this front away from the vulnerable parts of the ice sheet. So what Breyer's work has shown is that during the Pliocene, that bathymetric steering was overcome by warming. Those fronts jumped across this submarine barrier. And once they jump across that barrier, there's pretty much no bathymetric limit on how close they can get to these particularly vulnerable sectors of the East Antarctic and West Antarctic ice sheets. Now that's important because warm oceans are known to melt ice sheets from below, right? So where we see circumpolar deep water getting up onto the continental shelf around Antarctica, it has the capacity to eat away at this grounding zone and can accelerate ice sheet retreat, right? So that's the third thing we know. We know the ocean near Antarctica was warmer. And in fact, we also know that marine-based ice sheets were at a tipping point. So here we're looking at areas. So this is an update of that 1984 image that we looked at a little bit earlier. This is a 2013 visualization of the parts of the Antarctic ice sheets that are grounded below sea level. And as you can see, it's quite a lot of West Antarctica. So there are a few little islands that would be above sea level if all of that ice were stripped away. And then we have these key basins. You might recall that these are places where the ice sheet is rapidly lowering today. The Aurora Basin over here and the Wilkes Subglacial Basin over here. These are areas that we expect to be particularly vulnerable to the impact of that warm ocean sitting closer to the Antarctic margin. And we have some really nice records from the Antarctic Geological Drilling Program. Just here in the red star, and then that same IODP expedition, Expedition 318, where Breyer's record came from, sits here just at the mouth of the Wilkes Subglacial Basin. And when we look at those two sedimentary reconstructions, what we see essentially is that ice collapsed and readvanced with just subtle fluctuations in the tick-tock of the Earth's orbit every 40,000 years, 3 million years ago, right? So we understand that those marine-based ice sheets were at a tipping point where ice could regularly advance and retreat. Over here, I've got the Andril drill rig, Angie Fox, excellent scientific artist, has drawn the Andril drill rig in over the top. And you can see the way we have different sedimentary packages. So we've got glacial sediments at the bottom, sub-ice shelf sediment here in gray, open ocean diatom-rich sediment here in green, and then just repeated sequences of those stacking up as that ice sheet advanced and retreated and re-advanced and retreated and re-advanced, just with those very subtle changes in Earth's orbit 3 million years ago. So from that pair of expeditions, the two Andril drilling seasons and then IODP expedition 318, we now have really excellent evidence that both in East Antarctic subglacial basins and also in West Antarctica, we saw sort of wholesale retreat of the West Antarctic ice sheet, considerable retreat into the Wilkes subglacial basin, with pretty much every little tick-tock of that climate metronome the last time CO2 was at 400 parts per million. All right, so that tells us those ice sheets sat at a tipping point, and that it's a tipping point we're likely approaching today. And then the last thing we know from 3 million years ago, so that climate analog, is that sea level was quite a bit higher, actually. So the best reconstructions for sea level sit right around 22 meters higher than present day. There's significant error on those estimates, and they come from, some of them come from sort of past coastal scarps. Oh, I don't know where that's gone. Past coastal scarps here around the mid-Atlantic area of the US. There are also past sea levels in Western Australia that are identified in ancient shorelines. There are some perched coral reef records that are used to reconstruct that. And then also from the Wanganui Basin in New Zealand, there are 4M assemblages that we can use to, and grain size distributions that have been used to estimate sea level. And now where do we get, like where could we go to find 22 meters of sea level? Well, we're reasonably sure that there was no major ice sheet, continental ice sheet on Greenland. So that would account for about 7.4 meters of sea level. We have good indications from Andrel that most of West Antarctica retreated during those Pliocene peak interglacials. So that would give us another 3.3 meters. And that means that the rest would have to come from East Antarctica, right? That's really the only place we could go to attract that much additional sea level. So what does all of that mean for Antarctica and our Paris Agreement world? Well, from my perspective, it means that 2 degrees is definitely too warm for Antarctica, right? So when, when I think about where I sit in that sort of nexus between being like a neutral arbiter of the sort of best scientific evidence and a person who has responsibility to advocate for the best path for humanity, I think I come down on, because I come down in a position where some of the things I know I think are really relevant for where we go in the future. And it's my responsibility to communicate that as clearly as I can, right? So I can't, I can't tell the New Zealand government what the best way is to get our carbon emissions under control, but I can say that the best paleo science indicates that we really should be working hard to keep our warming under 2 degrees. And in fact, there are already indications that some of these processes that we see evidence for in the past are underway, right? So the ocean's circulation hasn't been this sluggish in 1,000 years, probably longer. Sea levels could be rising faster than predicted due to new source of Antarctic ice melting. Ocean heat waves are getting worse. Marine ice sheet collapse potentially underway for the Thwaites Glacier Basin. There's sort of compounding evidence every day that we're moving into a position where the Pliocene is an alarmingly good analog, or maybe actually we're moving beyond the Pliocene as an analog. So for me, that's an indication that it's been an urgent problem for some time, and the urgency is only increasing. So what does that mean for Paris Agreement targets? I would say it means we've really got to redouble our efforts to maintain that, like, we'll do our best 1.5 degree and not that hard ceiling 2 degree absolute warming. And that this is another artist representation of how that Ross Sea region, this is more excellent science art out of the Andrel program. So what we see today in the McMurdo Sound region versus what that might have looked like in the Pliocene, right? So this is not a place we want to be traveling ourselves. So all of that is to say, our decisions as climate scientists matter a great deal. This is just a little climate action tracker summary of what current policies track different nations along to in terms of compatibility with Paris Agreement climate targets. New Zealand has recently migrated from insufficient policies to highly insufficient policies. Australia is sitting simply at insufficient, so good work, you guys. This is something I think a lot about when I vote, I'll just say. So our decisions matter as individuals, and I encourage all of you to contemplate where you can, I guess, where your scientific passion can also lean into our, I guess, our societies making the best decisions we can. But I also want to say that our experiences matter. And this is something that, so I think a lot about the climate news, and climate news catches my attention. But the other kind of news that catches my attention is news like this, right? So in the last month, NIWA, that's New Zealand's sort of national atmospheric and oceanic organization, National Institute for Atmosphere and Water, have had a legal decision go against them based on a lawsuit filed by a technician who was sexually harassed by a member of their research vessel crew. And after the harassment was reported, he was promoted and she was not accommodated on a different shift. There's been a recent major report out from the US National Science Foundation highlighting that sexual harassment and assault plague US research bases in Antarctica. And, a fair amount of recent news about how discrimination and harassing experiences impact women in polar science, right? So that's the community that I align myself with. And so all of this is news within the last month and a bit, right? These are all just things that have been percolating to my attention. And every time I see news like this, it makes me reflect on how my personal experiences of harassment in the field have structured the progress of my career. And I feel really strongly that these sorts of experiences are pretty universal for women in this field. And I also feel like now that I am, I've been doing this for 20 years, I am in a position where they don't happen to me so much anymore, but I know they're still happening to other people, and where adding my voice to voices, acknowledging that this is a problem and recognizing that the only way it changes is if people who are in positions like me say it out loud and say it's not okay, and hold the organizations who, because the organizations who support science in Antarctica or science in other complicated and extreme locations are just like science in a lab. The organizations who facilitate that need to hear that this happens and that it needs to stop. So here's where, this is not an exhaustive list of my experiences, but this is a little bit of my experience, right? So I love the Pliocene. You can tell I've spent a lot of time thinking about the Pliocene. But before I really dug into the Pliocene, I spent some time thinking I might be sort of excited about the last glacial maximum and how it turned into the Holocene. And when I went on my very first major research expedition 20 years ago, right at the start of my PhD, so this wasn't in the US Antarctic program, it was in a different Antarctic program, but I had a really bad experience with somebody who was in a position of significant power at the national base that I was a guest in. So I was living in the US, I was studying in the US, I was invited to participate in a different program. Somebody in a really powerful position made that experience really difficult. And so I turned and I sort of retreated from that work and went a different direction. And then I thought, I'm super interested in how Antarctica first grew its ice sheets, right? So I would quite like to learn more about this Eocene and Oligocene climate transition. And so I got on a ship and I went to sea, and somebody in a really significant position of power on that expedition made my life really hard. And I was a little bit more prepared for him, right? So I had this bad experience. So this one, I was able to diffuse while we were still at sea. But it still made me feel kind of creepy every time I had communications after that expedition. And I ended up just not doing much with that science. And I also saw him turn his attention to a different young PhD student on the ship who left the field not many months after we got back from sea. Okay? So some pretty bad actors out there steering the course of my career. Luckily, I also had some really amazing actors in my life, right? So David, who got me excited about this stuff as an undergraduate, has continued to be a really super supportive mentor for me for my whole career. My PhD supervisor, also a super supportive, incredible mentor for me, and gave me a lot of space to think about how the processes we observe in the modern ocean are recorded in the paleo record. And then over here, Dave Mucciaroni, the lab manager in the lab I did my PhD in, super empowering, respectful person who mentored me and supported me for my whole career. But who knows where I could have contributed if these people hadn't derailed those parts of my curiosity. So yeah, so that I think is important. It's important to me that other people know this happens to a lot of us. It's important to me that anybody, the more I hear and read other people talking about their own experiences, the stronger I feel to consider, to consider what I've experienced, and to, when I read about this big NSF report, one of the first things I did was get in touch with the New Zealand National Program to ask them for information about how we are protecting our people and our young researchers, and how we're offering training to everybody who goes south with the New Zealand Antarctic program, to ensure that people who are bystanders and observers feel empowered to act, and to ensure that the folks who might believe they're acting in good faith but are actually behaving in harassing ways have an opportunity to explore their own behavior, and to ensure that anybody who does receive unwelcome advances knows that they have space and support to push back against those. So that's one of my new crusades, is to say it happens and it shouldn't, and to start holding my organizations accountable for educating people so there can be less of it. And speaking to Womeesa, I want anyone out there who's had an experience like this to know that far out, they're really common, and they can be really demoralizing, but also that they, that there are a lot of people who will support you, whether you ever want to report or if you are just happy to hear that and experience it, and know that there are people who know you're not alone in that. So, and I've again taken speaker prerogative to overrun my time, and I am grateful to you for giving me a space to acknowledge that people like that can't diminish the importance of people like this and of people like us. So I'll say thank you now, and I will compose myself a little bit, and I'm happy to answer any questions about anything at all. So thanks, guys.